In the last class, we have been discussing the lattice model of solutions, and we have already went halfway through the derivation of the expression for the Helmholtz free energy density. So, I will quickly recap that derivation we have been doing, and then we will take it further and complete the derivation that we have been working on. So, just to recap, we are working on the lattice model of solutions, where we assume that we have certain number of solute and solvent molecules in the system which are constrained to move on a lattice instead of moving everywhere in 3D space. And the representation I was using was some red color circles for the solute and green color for the solvent. And of course, both of these are assumed to occupy the same volume, that is equal to the lattice volume that is equal to the cell volume in the lattice. So, until so far what we have done is we have derived within what is known as the mean field approximation, that assumes that all configurations have the same energy EI. Within that approximation, I said that the partition function, which generally is the sum over Boltzmann factors of all configurations I, with all configurations with energy EI. If I assume the EI approximately equal to the mean energy, I can write this as W multiplied by exponential of minus beta E bar, and we can get W, that is the number of configurations, by simple combinatorics. It is NP plus NS factorial by NP factorial NS factorial. And also we derived the expression for E bar as half n tot z epsilon pp phi square plus epsilon ss 1 minus phi square plus epsilon ps with a 2 in front, phi multiplied by 1 minus phi. Okay. So, if you look at this particular term and keeping in mind that ultimately I am interested in the free energy F, and actually divided by volume of that quantity F by V, and in that quantity I only care about the quadratic terms in phi, and the reason is because ultimately the behavior of mixing and phase separation is dictated by the second derivatives. So, since we only care of F double prime for mixing or phase separation, we can drop all the linear terms that are terms containing either phi or a constant, that we can drop because anyway we are interested in second derivatives. Okay. and if that is somewhat confusing to you, you can try doing a separate derivation starting from the terms we have ignored, and in the end you will see that those terms are really having no significance in the larger scheme of things, because ultimately we are going for the second derivatives of the function f that I will derive. So, I will collect the terms that contain second power of phi, that is epsilon pp phi square here. So, this term will retain. So, let me write on top what will retain. In the second term, there is epsilon ss phi square, and then we have two more terms which are of lower order, they will be ignored. And similarly, in the last term, we have 2 epsilon ps phi square, and we also have a 2 epsilon ps phi, which is a linear term, and we can ignore that. So, using this idea, I can get the expression for E bar. So, again, if you have any confusion, you can try retaining the linear terms and continue derivation, and then see how does it affect the end results with regard to the mixing and phase separation behavior that we are going to discuss. And what you will find out is that dropping the linear term has no consequence in the final results that we are after. So, what we get is E bar now is half n tot z phi square multiplied by epsilon pp plus epsilon ss minus 2 epsilon ps, which you can confirm by looking at what we had earlier. This entire quantity I will call as some delta epsilon, and then this thing becomes half n total z phi square delta epsilon. So, before we go further in derivation, let us pause for a moment and try to see like what does this delta epsilon signify. Okay. So, we are interested in the total energy of the system, and that energy is composed of solute interactions, solvent interactions, and solvent interactions. And so, in delta epsilon in some sort represents the effective interaction that is present in the system. Okay. And now, of course, this E bar does not contain the entropy contribution, the entropy will come separately. This contains in some sort the energetic or enthalpic contributions, but in any case, if this E bar is highly positive, that would mean that the system will not like to mix, it will have a tendency to phase separate. On the other hand, if E bar is very negative, that would mean the system will have a tendency to mix. So, this delta epsilon in some sense characterizes the enthalpic part of energy, and we will take one step further in a moment. So, what exactly it characterizes? So, let us see, let us think that we had the following arrangement or a cross section of the system that we started with, which was all solvent molecules, and in between we have, so let us make it like this to begin with. So, we have a solute here as well, and we have a solvent in the middle, and then we have two solutes which are right now separated, they are not together. And let us say we are thinking about a process where these two molecules will come together. So, in that case the new arrangement will look like this. So, once these two red guys, these two solute molecules come together, this will be the new arrangement. Now, let us think of like what is the energy gain or loss that happened as a result of this particular process, where the solute molecules which were a bit farther came together and formed a new pair. Okay. So, this is energy of formation of one pair. Okay. So, now if we look at this particular arrangement, what you will notice is going from left to right, we formed one additional pair of solute, and then since this guy moved here, the solvent moved here, it also formed a new solvent pairs between these two. You can see like all the other pairs between solute and solvent remained unaffected except the ones I am looking at. And then you can also see that there were two pairs between solute and solvent which had to be sacrificed as a result of this process, because the solute molecules came together, they formed one contact. So, we gained an energy by one contact of or one pair of solute, one pair of solvent minus two pairs of solute and solvent that we had to sacrifice. So, the energy change in this process is then one pair of solute, one pair of solvent minus two pairs of solute and solvent, and of course, this will be favored when this entire quantity is less than 0, and this quantity is, by the way, my delta epsilon. So, if delta epsilon is less than 0, I will tend to form more pairs of solute and solute, which if you now think of more number of solute molecules, if the system favors the formation of solute pairs, that means system has a tendency to phase separate. Okay. So, this essentially means a tendency to phase separate. Okay. Now, what is interesting here is the following, that the phase separation or the delta epsilon is not really dictated by the solute interactions alone, they are also dictated by the solvent interactions. So, what happens, for instance, if epsilon SS is like very negative, and let us say epsilon PP is 0, epsilon PS is also 0 or close to 0. So, although the solute does not interact with the solvent and there is no interaction between solutes, even then we can have phase separation, because the solvent like itself much larger. This is an example we have been giving about the hydrogen bonding in water. If the interaction between water molecules are so large, then any solute which does not offer an energetic contribution in terms of either a solute solvent interaction or a solute solute interaction will have to phase separate. That is of course a limiting case, because most of them will have some favorable interaction, let us say a hydrogen bond with water and so on. Okay. So, the key lesson from here is, when we talk about the interaction between solute molecules, and this is not an example of polymer right now, this can be any solution, when we take interaction between solute molecules, we have to think in an effective way, in a sense that how are the solvent interactions and solute solvent interactions also affected by the contact of solute species. Okay. So, in the polymer physics language, we define a quantity named chi, that is called a solvent quality. Right now we are not doing a polymer solution, but let us say at least define the quantity. The quantity is defined also for a binary solution, so that we can use it more effectively when we discuss about polymer solutions. So, we will define a quantity called solvent quality chi, that is defined as minus z delta epsilon divided by 2 kBT, and I can plug that in here, and that I will have E bar is equal to minus n dot chi phi square, and now this is E bar by kBT. Okay, because in any case we do not look at the interaction values by themselves, we look at how they compare to kBT, that is a thermal energy. Only if the energy is very high compared to thermal energy, it can have any effect on the system, because otherwise the system is entropy dominated and favors mixing. So, let us keep that aside for a moment, and let us go back to the expression of Z that we started with. So, Z is now W exponential of minus beta E bar, and I know by the statement we have made earlier that the Helmholtz free energy is minus kBT of ln of Z. From here what do we get is minus kBT. So, ln of Z will be ln of W minus beta E bar from here. So, we have minus kBT ln of W plus E bar, because beta is anyway equal to 1 by kBT. So, this we can identify as E bar minus T multiplied by kB ln W, and this quantity, as stated by Boltzmann, is the definition of the entropy. So, Boltzmann really had a very funny life. He derived this particular expression, and no one agreed to that this expression of entropy, and while he was living. Only after he died, people saw value to his work, and this expression is engraved on his grave as equal to kB ln omega, omega for W, which was one of his most important contribution to today's thermodynamics. So, we just multiply the Boltzmann constant. So, of course, he did not call it a Boltzmann constant, he called it a constant k, by the logarithmic of the number of possible states the system can have. We get an expression for the entropy of the system. This is the Boltzmann formula. Now, it is known in the thermodynamics. So, now you can see this expression we have is E bar minus Ts. You can compare to the standard thermodynamic expression F equal to U minus Ts, and note very clearly that U is basically my E bar and Ts appeared as it is that we had there. Okay. So, although when I first defined this quantity, I did not make any particular link to the expression right here, but now you can see for yourself that this is what it is. The E bar is some sort of internal energy of the system. Only thing is that it is derived in a mean field sense in the theory that we have discussed, where we assume that all the configurations are having the same energy EI. Okay. So, now we know what W is and we know what E bar is. So, let us first look at ln of W. W is Np plus Ns factorial by Np factorial Ns factorial. So, ln of W will be ln of Np plus Ns factorial minus ln of Np factorial minus ln of Ns factorial, and we will make use of what is known as the Stirling formula. We had already used it in the context of random walk. So, for large n, the ln of the factorial can be approximated as n ln n minus n. There was one more term there that we are also ignoring, that is anyway a smaller term compared to this. Okay. So, using this formula, what we have is Np plus Ns ln of Np plus Ns minus Np plus Ns minus Np ln Np plus Np minus Ns ln Ns plus Ns. They will cancel, and now we have Np plus Ns ln Np plus Ns minus Np ln Np minus Ns ln Ns. This I can write as minus Np ln Np by Np plus Ns minus Ns ln Ns by Np plus Ns, and this by definition is my phi. So, this has to be 1 minus phi, and so we get ln W is approximately equal to minus Np ln phi minus Ns ln 1 minus phi. This is what we have derived from here. Okay. So, now you can note again that ultimately Np is equal to n tot of phi and Ns is equal to n tot of 1 minus phi. Therefore, ln W is approximately equal to minus n tot phi ln phi plus 1 minus phi ln 1 minus phi. Now, I will go back here, put the expression of ln W here. So, it is E bar minus kBT ln W, and E bar we have already obtained right here, minus n tot chi phi square multiplied by kBT. So, using all of this, what I get is F is equal to E bar minus Ts is equal to E bar minus kBT ln W is equal to kBT into minus n tot chi phi squared plus n tot phi ln phi plus n tot 1 minus phi ln 1 minus phi. I can take n tot also common, okay. So, now we have expression for F, and I have to divide this by volume to get the Helmholtz density. So, F by V is simply F by n tot multiplied by Vc, where Vc is my cell volume, that is taken as equal to the volume of solute and solvent molecules. So, we have cancellation of n tot in this expression, and that what we get is kBT by Vc phi ln phi plus 1 minus phi ln 1 minus phi minus chi phi square. Okay. So, this is what we have got after we have dropped the linear terms in the energy expression. And now, I will play a small trick just for the expression to look slightly nicer. I will add some arbitrary linear term here. Okay. We will see advantage of this in a moment, but basically we will add a term here which is a linear term which has no consequence in mixing behavior, in mixing or phase separation behavior. The reason why we have added it, the first reason is that now the expression looks somewhat symmetric, because now I can write this as so it is easier to remember, but more importantly you can see there that if I switch phi by 1 minus phi, I do get the same result. So, we will have 1 minus phi ln of 1 minus phi plus phi ln phi plus chi multiplied by 1 minus phi multiplied by phi, that will be the same result that we have here. So, if I look at the function plot, that will have a symmetry around phi equal to 1 by 2 So, we have a mirror symmetry because if I simply replace phi by 1 minus phi, I get the same result. So, it must be symmetric with respect to phi equal to 1 by 2. So, the advantage is if I now draw a common tangent, sorry for the poor drawing, it will look straight. So, let me draw it again so it looks somewhat more symmetrical. So, you can see if I draw a common tangent now, that common tangent will be a horizontal line which correspond to f prime is equal to 0, and that simplifies our calculations. Okay. So, by adding a linear term, we got this particular advantage in terms of our equation. So, now just to conclude, we have been able to find this expression for the Helmholtz free energy density, that is a function of phi and t, and which is a symmetric expression, and using that now I can go on and find the binodal, spinodal and critical point and so on. And again, based on that theory, we will go ahead and try to extend that to the polymer solutions. With that, I conclude here. Thank you.